Yes, yes. Here we are, very close to solar maximum, and it appears that solar maximum is going to occur a little earlier than we thought. Perhaps by the end of the year, perhaps the first quarter of next year. And of course, this is a time where there's a lot of solar activity, a lot of coronal mass ejections and flares, sunspots galore, and if you're living in the right places, aurora. Not to mention the threat to astronauts, but we won't go there just yet. We thought it would be good to talk about the sun a little bit. And it turns out that you can understand an awful lot about the sun if you just understand sunspots. Okay, so we're going to talk about the sun today, and this may be a little bit long. We may have to cut this and turn it into a two-parter, but let's give it a go. Let's see where we end up here. Okay, so here's the sun that you might expect to see if you have a small backyard telescope with an appropriate solar filter. That's our disclaimer, with an appropriate solar filter. And the sun will look different colors depending on the filter. Daz already walked us through how nobody really knows what color the sun is. There are different correct answers. But one of the things that you can see in this image is that the edges of the sun are dark, right? And this is actually real. This is called limb darkening. And it has to do with the fact that the sun is gaseous. And so you can see through parts of it at different depths. And some SOME light gets through at the upper regions and less light as you move down. So this is actually a real image. And if you look on the bottom, you can see a tiny sunspot there. Okay. And we've only understood this for about 400 years when Galileo saw sunspots on the sun and he said, there are spots on the sun, and the church said, no way, there are no spots on the sun is pure and pristine. And Galileo proved them wrong, which probably wasn't a good thing to do, but
dangerous thing to do.
The rest is history, as they say.
Yeah.
Here's a little bit better image of the sun. Again, this is in what we call white light. In other words, all the colors of the spectrum that our eyes can see kind of mixed together to produce a white image. And so now we can really see some sunspots. And you'll notice that they have structure. They have different densities. There's a dark inner portion and a lighter outer portion to these sunspots. You might even notice that they tend to occur in pairs. Well, this is all very important information because it helps us understand sunspots. And we're going to figure out why all this is true in just a few minutes. I think this was supposed to be a video, actually. So I'm not sure what to do with this. I think I'll just move on because it doesn't do what I want it to do.
The sun never does.
It does, yes. They're like comets or cats.
Yes. Or Perseids.
So, here we see 6 images of the sun, right? And these are 6 perfectly good images that all look completely different. And most of the reason for this is that the sun and all other objects in the universe look very different depending on the wavelength of light that we use to view them in. In the upper left, we have X-rays. The sun in X-ray, this is taken, of course, above the atmosphere because X-rays are absorbed by our atmosphere, which is a really good thing. And so we're seeing very hot regions of the sun. We're seeing into the corona of the sun that can reach 1.5 million degrees centigrade. Further just to its right in the blue there, by the way, these are colors we made up because we can't see these colors. We see the sun in ultraviolet light, again, from above the atmosphere because very, very tiny amounts of UV radiation make it to the surface of the Earth. So here we're seeing a little bit lower down into the atmosphere, a little cooler. We see a white light image, or V for visual image, on the far upper right. A hydrogen alpha image down below. This is just a very specific form, very restricted format of red light that deals with a transition of electrons in the hydrogen atom. And then infrared and radio. And so the point here is that objects in space look different depending on the wavelength of light that you're using to view them in. In fact, objects on the Earth look different. Well, here's an image of the sun, right? If you're an amateur astronomer, perhaps even if you're not, this is an image of the sun with the moon right in front of the sun, causing a total solar eclipse. So you see the moon is very dark here, and on the outside you see the very soft, tenuous solar corona that you can't see normally because the sun, the photosphere of the sun is just too bright. But look carefully, you can see some structure in the corona. And that structure is reflective, is evidence of the sun's global magnetic field. The particles in the solar corona, many of them are charged particles, and so they are attracted to magnetic field lines. And that's what you see here. The corona is glowing, being attracted to the field lines, and so that gives us that allows us to see some of the sun's magnetic field. That's important for our understanding of the sun and sunspots. So hang on to that. So I've given a lot of talks about the sun, and sometimes they just get so esoteric. And so it occurred to me one day that if you just understand 5 things about sunspots, you can basically understand the entire sun and how it works. So 5 things about sunspots. They're dark, as we have seen. They're cool. So I have Joe Cool on the right-hand side there to remind us. They're highly magnetic. They're associated with solar storms, coronal mass ejections, and flares. And the number one thing to understand about sunspots is they come and go in cycles. So you have the bicycle down there for the,
Don't give up your day job.
Can remind us. So we'll just go on for now. Okay. When we look carefully at sunspots, and this bottom image, by the way, is a ground-based image from a solar observatory, maybe National Solar Observatory, we see that it has structure. It has a dark inner portion and a lighter outer portion. The umbra is the inner portion, the penumbra is the outer portion. And outside of that, we see the bubbling, I'll call it the surface of the sun. It's the what we generally call the surface of the sun, the photosphere, as heat is rising, the sun trying to equilibrate with its surroundings, get rid of its heat that's being generated in the core. So sunspots definitely have structure, and we're going to talk about why. Here's another image of a sunspot up close, just like the one we saw before. The inner darker part, the umbra, is cooler than the surrounding area, the penumbra, which is also cooler than the surface of the sun. Surface of the sun, let's see, we have mostly UK people. So do you guys use centigrade, Fahrenheit, Kelvin? What do you use? It's about 6,000 degrees centigrade. And the inner portion of sunspots may be 3,500, 4,000 degrees centigrade, something like that. And we're going to learn why they're cooler. Well, this was supposed to be a video too. Heck with it. Let's move on. Okay. We have very good evidence now from the physics and from observations, especially a field called helioseismology, which is looking at how the sun rings as sound waves propagate through it, that we can look at the sun as being composed, at least from the photosphere down, into 3 parts: the core, the radiative zone, and the convective zone. In the core, where temperatures can reach 15 million degrees centigrade, centigrade Kelvin doesn't matter at that level, we have fusion taking place where 2 protons are fired together at very high speeds because of the high pressure and temperature to bond together, to bypass that repelling force and actually fuse together. This cannot happen in classical mechanics. And all of the physics that we learned in up to the 1800s, this cannot happen. But we know now through quantum physics that this does happen. So that produces the gamma ray photons that begin in the core of the sun. They migrate out into a region called the radiative zone where they are scattered by electrons, free electrons in that zone. And they're scattered so much, just kind of like a drunk man's walk, if you've heard of that, that it takes on average, statistically, about 100,000 years for that single gamma ray photon to get out of that radiative zone of the sun. 100,000 years. As you move out from the center, it gets cooler and cooler and cooler. And so all of a sudden, you can form atoms. You can have electrons kind of hanging on to nuclei. And as things cool, the most effective means of heat transport is convection. And so they form these convective cells that rotate. And those gamma ray photons hitch a ride on those convective cells, reach the surface of the sun, and then it's 8 1/3 minutes to get to the Earth. Okay. We know sunspots are dark. I've told you they're magnetic, but how do we know? One of the ways we know is that we see a quality when we look at the spectra of sunspots. We see a quality called Zeeman line splitting. Zeeman line splitting. And it means that spectral lines in the presence of very powerful magnetic fields will split into 3 parts. And we see this visually here of a spectrum where a spectral line has split. That is observational evidence that these sunspots are very magnetic. And the reason they're magnetic is that the sun rotates. But it doesn't rotate like a solid sphere. It rotates like a kind of gloppy, gas. And so the equator of the sun rotates once every 27 days or so. And it's rotating faster than the upper and lower latitudes. So the magnetic field of the sun gets dragged around time after time, month after month after month, until it gets really tangled. You might imagine having if you knit, I don't know how many of you knit, but if you have a big piece of yarn and it's all kind of, clumped together, and you throw it in the bottom of your closet, that piece of yarn might have a little piece of yarn sticking up over all the rest of them, just a little piece. And that in the sun would be a sunspot. And since that little loop of magnetic field is looping above the sun, you have one side and the other. You have a north and a south pole, because magnets have north and south poles. There are no magnetic monopoles. So the sun is sunspots are magnetic, and this is really important. Just an image of the sun in ultraviolet light, showing many, many active regions on the sun. You can even see little loops. If you look on the edges of the sun here, you can see little loops of this plasma. And this is the material rising from a sunspot, from one side of a sunspot, and diving back down into the other, because these plasma obey magnetic field lines, just like as we saw before. So why are they cool? They are relatively cool. And the reason is that the magnetic field in the region of these sunspots is pushing down on that gas that's trying to upwell to the surface. Remember the convective zone just under the photosphere? And since they're pushing down on this gas, it can't get out there, so it has to move around the sunspot and emerges on either side of the sunspot. But the sunspot region itself is cool as a result. Now, okay, this is my favorite slide because it has a little equation in it. And it's actually not that hard to understand. It turns out that a small drop in temperature produces a large drop in brightness. So we just said sunspots are cool, relatively cool. In this equation, L is luminosity or brightness, and it equals 4, that's a number, times pi, that's a number, times radius, which is just a number, times sigma, which is a number, times the temperature to the 4th power. So you modify the temperature just a little bit, raise it to the 4th power, and you have a huge change in brightness. And this is why sunspots are so dark, because they're cool. It also turns out that solar storms, and we're seeing a lot of solar storms these days because we're very near solar maximum, solar storms tend to occur around large sunspot regions. Solar flares, which are generally dominated by electromagnetic radiation, and coronal mass ejections, which are dominated by particle radiation, they tend to occur around sunspot regions. So during solar max, we see lots of sunspots, bigger sunspots in general, and more solar storms. No accident. So, what have we learned about sunspots? They're dark. We know why they're dark. They're cool. We know why they're cool. They're magnetic. We've seen evidence of that. They're associated with solar storms, just because I told you. And and they come and go in cycles, but we haven't talked about the cycles yet. Let's see if I have a.
That's fantastic.
Where are we in time? I don't know how to break this up quite.
We've got it. Well, we're half an hour into the show.
Okay. I wonder if well, you let me know. You have a hook. Andy has the hook, and he will hook it around my neck and drag me off as I wave to screaming fans.
Right. Well, I mean, it's all interesting stuff, Lou. So we would love to see it. So no problem at all. Yes, indeed. Right. Well, thank you for that.
Perhaps we'll carry on next week with the rest of us.
Yeah, we can carry on next week.
Yeah, because I mean, Lou, you mentioned the corona being up to 1.5 million degrees in heat, hotter than the actual surface of the sun. Well, just recently I was reading a paper that they think they may have solved that problem, why the corona is so much hotter. And it was, I'm not sure whether it was Betty Colombo or Parker Solar Probe, one of the two.
No, it was the studying Solar Orbiter.
Oh, okay, then not even the one I was thinking
Europeans always want to take credit. I mean, come on.
For good reason. We just do it better, that's why.
Of course.
Yeah. What they noticed was that you were talking about these magnetic lines on the surface of the sun, which usually join the spots and all that, but there's also other magnetic activity going on, which gives us the plages, which is the light areas. So there's a lot of magnetic activity going on. But what they found is that it's covered in these little magnetic lines, which apparently are vibrating very rapidly. And they think that this vibration of all these small magnetic filaments is possibly the cause. And like I said, it's possibly, with the sun, we don't know positively, is what's actually heating the actual corona to such a high temperature. And if it's correct, then that's one more nail in the coffin of the mysteries of the sun.
If you remember, Daz, I was showing some images of those last week. And they're like,
oh, of course, yeah, sorry, yeah.
No problem. They're like little magnetic waves that are traveling rapidly across the surface of the sun. And they think that's what's, as Daz said, that's what's heating the corona.
Would these be the Elfin waves? That this was the prevailing theory before Parker was launched.
Don't know.
I couldn't tell you offhand. But also, you were talking about the cycle. Of course, we were expecting cycle 25 to reach its maximum on 2025, but because it's the prediction. This is outdoing all the predictions that they've made so far. They expected the solar spot activity to be very low, like the previous cycle 24 was. And they were then, of course, there was also some people that were expanding that. If we go into what they call it, a great solar minimum, which could eventually lead to an ice age. Well, that'll sort out our global warming problem.
I have to break in here. We have been laboring under that theory for a long time. Regions of time where there are essentially no sunspots, Maunder minimum, and all that, and the ice age that occurred in Europe during the last one, I think the late 1600s. That appears not to be the case any longer. That a more careful review of the data. I was teaching it. But a more careful review of the data suggests that sunspot minima, even prolonged sunspot minima, do not result in mini ice ages as much as we need a mini ice age right now. I don't think that's borne out by the data.
Not happen. Not from that anyway. Oh, that's a shame.
Yeah, because the second minimum you were talking about, was that the Dalton minimum?
Oh yes, there's
yeah, there was a Dalton. Okay, so that's burst that bubble anyway. But of course, we've got an average of these cycles is 11 years, but they can vary to be as short as 8 years and up to 14 years, I think it was. So the 11 year is an average. And of course, if we're going to go to maximum the end of this year, because the solar spots have appeared a lot more than we were expecting and so much quicker, that because if you see a graph, you can see there's a little hump, and the 25th of 2025 was the maximum. Then it's supposed to come back down again. The actuals, if you look at what the actual sunspots have gone, it's actually above the line and climbing still at this very moment. So if we do go to a maximum at the end of this year, it would be interesting to see whether that means we're going to get a very long decline to a minima to cover sort of like more towards the 11 years, or we're going to have a very short cycle. It's fascinating to see it actually pan out, how it's actually going. So it just goes to show that we really, although we know a lot about the sun, we don't know enough to predict anything at the moment. So yeah, it's, as you said, it's very, very interesting.
The problem is that there are two ways that we can make predictions outside of Ouija boards. One is to look at the previous behavior of the sun, right? And we had seen that the solar maximum had been declining over the previous cycles. The other, which would be much more accurate, would be to actually understand the solar cycle, why it is the way it is and what drives it. I mean, there's some thinking that gas moves latitudinally and dives down to the tachocline region below the photosphere and all this stuff. And we don't really understand it. But if we understood the physics well, then we would be able to predict with better accuracy. And we just don't yet.
No. I mean, one thing I did forget to mention is we could also have a double peak of maximum. It can start to decline and then pop back up again. So it's fascinating. I find these sunspots and these cycles. And of course, I think it was Ian mentioned it last week when we mentioned the sun, is that at the end of this cycle, the poles will swap. So that's one of the ways we know that the cycles come to an end. And also with your dual sunspots, they've got polarities. They will also swap. And that's how we know we've come to an end of a cycle. But then you've then got supposedly another cycle. And I think really we need to look at not the 11-year cycles, but the 22-year cycles when things have changed, because there has been some predictions that what they call a south lead cycle tends to have have more interaction with us than with solar weather than a north one does. It's just fascinating. I find this so interesting. And if anybody wants to know a little bit about, I mean, Lou's done a wonderful job as regards telling us about the sunspots. If you look at on the YouTube and look at our the presentation, which was does the solar cycles interact with earthquakes and volcanoes on Earth, have a look at that, and that'll give you a brief description of how these cycles work. So,
and can I just say as well that sunspots are not unique to the sun. We have actually observed them on the surface of other stars. So we know that they are a common feature of stars, that they are sort of intrinsic, if you like, to the activity of stars. For example, here's one on the surface of, let me just make that a bit bigger, of Zeta Andromedae. You can see 3 clear, well, astronomers call them star spots, of course, not sunspots, because they're not on the sun, they're on other stars. So these are star spots, and this is another star, big star called Zeta Andromedae. And I think they've imaged them on Betelgeuse, Regulus, and Antares, if I remember right.
Yes.
I mean, sorry, Andy, as well as sunspots, you've also got to think about coronal holes, which also give us intense space winds. And Kevin here is talking about plages and faculae. There's a lot of things that actually go on the surface of the sun, which all interact, and they all do their own thing. I mean, there's been a couple of this week alone, we've had about 3 or 4 storms come our way from flares and coronal mass ejections. So it's really ramped up at the moment. And if you want to look at this, a website which I've just found recently, it's called solarham.net. Now, if you go to that, you'll be able to look at the sun in different wavelengths, as Lou was pointing out. Every wavelength gives you something different to look at.
What's it called,
and it's solarham.net.
Solarham, as in H-A-M.
H-A-M, yeah.
Okay.
And from there, you can actually link up to NOAA, which is the North American space weather community, or just Google NOAA space weather, and there's one on there called panels. And if you go on the panels, it gives you all these graphs, all these diagrams. And if you go to the actual NOAA site, you can actually watch videos of what's happened in the last few hours and things like that. So and it's all free. So have a look. It's fascinating.
Right.
You can spend hours on it. Anyway, I'm waffling now.
So what
sorry.
we'll do now?
Yeah, lovely talk, Lou.
What we'll do now? We will move celestial objects a bit closer to home. We'll move from the sun to the moon.